So we are moving on to the next topic, that is efficient computation of DFTs of two real sequences. Now when we look at this particular topic, what it basically refers to is a mathematical derivation, and along with that we have to do a numerical. So we begin with few assumptions. We are going to consider two real valued sequences, x1 of n and x2 of n. These are the two sequences. Now what we are trying to do here is we are going to find out the DFTs of x1 of n and x2 of n with computation by combining these two sequences and computing the DFT of the newly created sequence. So instead of doing it two times, we're doing it just one time, and we are going to learn how it can determine the DFTs of the individual real sequences. So we have these two sequences x1 of n and x2 of n. We are creating a new sequence x of n, which will be given like x1 of n plus j x2 of n. So if we are having the sequence like 1 2 0 1, which is x1 of n, and if we are having another sequence x2 of n equal to 2 2 1 1, what we ultimately do here is we are creating x of n, which will have four components, which will be as follows: 1 plus 2j, where x1 of n is corresponding to 1 and 2 corresponds to x2 of n, and it will result in 1 plus 2j. Then we will have 2 plus 2j. Then we will have j, ultimately, because there is no component real part over here and only j exists over here, and the last one will be 1 plus j. So this will be the newly formed x of n sequence. We are going to create the conjugate of this particular sequence because it will come into role at a later point of time for our understanding. So x star of n, it can be given as 1 minus 2j, 2 minus 2j, minus j, and 1 minus j. We'll come into it later, or why this particular sequence is coming into use, or we could explain it right away. The use of this particular sequence is to determine x1 of n and x2 of n. I hope this statement makes sense to you. If I write x1 of n is equal to x of n plus x star of n by 2. If you want to prove it, if you want x1 of n, that is x1 of n is 1. So if we have x1 of 0 is 1 actually. So if you want to determine that, this will be equal to x of 0 plus x conjugate of 0 by 2, which would imply x of 0 is actually 1 plus 2j, and plus x star of 0 will be 1 minus 2j. When we combine it, it becomes 2 by 2, it becomes equal to 1. So x1 of 0 is equal to 1. We have determined it. Similarly, you can find out x1 of 1, x1 of 2, and x1 of 3. Now to bring it in the other way, how to determine x2 of n, it will be given by this formula: x of n minus x conjugate of n whole divided by 2j. Let's see how it works. So if you want to find out x2 of 0, which is eventually 2, what we have written here is it is x of 0 plus, x minus of x conjugate of 0 by 2j. So x of 0 is 1 plus 2j, x conjugate of 0 is 1 minus 2j, we have divided it with 2. So this will be like 4j by 2j equal to 2. So I hope this makes the sequence or the definition of this particular sequences explained over here makes sense. So x1 of n can be written as x of n plus x star of n by 2, and similarly x2 of n can be written as x of n minus x star of n by 2j. So by linearity property, we can say that if x of n, already we have established this relationship, x of n is equal to x1 of n plus j, x2 of n. By linearity property, we can say that x of k will be equal to x1 of k plus jx2 of k by the linearity property. Similarly, we can rewrite the equation for this entire x1 of k and x2 of k based on these two equations. So x1 of k can be written as x of k plus x star of minus k by 2, and x2 of k can be written as x of k plus x star of k by 2j, where dft of x star of n will be equivalent to x star of minus k. So this can be considered, and we move ahead with this particular topic. So based on our assumptions of the sequence x1 of n, x2 of n, we can write x of n as 1 plus 2j plus 2 plus 2j plus j and 1 plus j. These are the 4 terms of x of n. Now we need to find out the DFT. To get along with this topic, we need to find out x of k, which is a DFT of x of n, and that can be found out using the transformation matrix method, which we have done over here. So you have 1 1 1 1 along the row column. This was already a part of the first module, and you can know about this matrix from that particular video over there. And using this matrix, we find out the solution. So this becomes 4 plus 6j, 2 minus 2 and 2j. So this is a DFT of this particular sequence. So we have x of k, and from this we can find out x1 of k and x2 of k. So for that we need to solve this particular thing, we need this equation. X of k, we already have it, so we get x conjugate of k, which is 4 minus 6j, 2 minus 2 and minus 2j, and we get this. We have to derive, but we have to derive x star of minus k, which is a folded version of this thing. So if we consider this signal to be drawn in a circular manner, if we consider it to be folded along the horizontal axis, the change that comes along is the one at this portion interchanges over to this point, and the one at this point comes to the top. So eventually our signal, it becomes 4 minus 6j minus 2j minus 2 and 2, where the switching happens between these two components. So we can find out x1 of k and x2 of k using this these two solutions that we have. But in order to verify the answer, we can compute the DFT of x1 of k, which will give you the result 4 1 minus j minus 2 and 1 plus j. This is a DFT of x1 of n, which is assumed to be 1 2 0 1, and this is the DFT of x2 of n, which is 2 2 1 1 6 1 minus j 0 and 1 plus j. This is just for verifying the answer that we are going to determine. So x1 of k, as per the equation that we had drawn earlier, or derived earlier, it is equal to x of k plus x star of minus k by 2. So when we substitute the appropriate values, we get x1 of 0 as 4 plus 6j plus 4 minus 6j by 2, resulting in 4, which is exactly the same result as we have got over here. Similarly, you'll be getting 1 minus j minus 2 and 1 plus j out over here. And for the next counterpart of x2 of k, it will be x of k minus x star of minus k by 2j, whereby if you perform this operation correspondingly, you will be getting it as 6 1 minus j 0 and 1 plus j, which is the result that we have obtained over here. So this winds up the topic, and we just have numerically as well as theoretically conveyed how efficient computation of DFTs of two real sequences can be carried out by combining them into one complex sequence.